Okay, welcome back. I hope you had a good break. We're going to crank it back up and see how it goes. This week should be pretty easy for you. I'm going to give you an assignment that's due on Wednesday, and that is to watch this video, and then there's a Google Doc, and you'll just fill in the blanks, and I'll try to give you all the answers in this. If I fail to do that, or you fail to understand it, you can come to office hours, or you can always, I'm going to give you, along with the Google Doc with the, there will be a reading with blanks in it that you'll fill in, and a Google Doc where you write in your own answers. Everybody gets their own. You don't have to make a copy. So you'll submit that to me when it's done. It'll just be a list, I think it's 1 through 28, and you just write your fill in the blanks on that. Should be pretty obvious. I just finished making this video once, and it came out to 12 minutes, and after discussion with Carson, I'm going to not have any videos that long. So this will be shorter, so I'm going to be paying more attention to what I need to say and talking a little bit faster. Okay, so what is this about? It's a review, and what we've been studying is atoms, and this is going to be about atoms, and what are the things that you should know about atoms so far, because we're going to use those to build on our knowledge, or your knowledge. Okay, so we know that atoms are really, really small. First of all, we know everything is made of atoms, so because that's going to be the answer to question number 1, or blank number 1 is the smallest piece of matter that exists alone is an atom. And you can say, well, what about a proton? What about a nucleus? What about an electron? But those things don't exist independently. They only exist as part of an atom. So an atom is the smallest thing that exists alone. They're tiny. They're almost completely made of empty space, right? I know you couldn't hear me very well when I was out on Natowich Field pointing at snowballs and stuff, but atoms are almost nothing, right? If they packed atoms more tightly, then you could fit Mount Wantasket into a peanut butter jar. It's sort of one of the okay, blah blah blah. I'm gonna keep this short, so I'm gonna stop talking about that. So what else? We know that every nucleus has a positive charge because it has protons in it. Protons have a positive charge. They're the only thing in the universe with a positive charge. If it has a positive charge, it's either a proton or it has a bunch of protons in it, more protons than electrons. So there are different kinds of atoms. I'm going to give you a periodic table, and on the periodic table are all the 92 kinds of atoms that exist in nature. And 2 that I'll often refer to are number 6, carbon, and number 8, oxygen. Those are just among my favorites. And carbon is number 6 because every atom in the universe that has 6 protons is carbon. Every atom in the universe that has 8 protons is oxygen. Okay, so that's called the atom number. The atom number is how we identify them. Every kind of atom has its own atom number, and that is the number of protons. Also the number of electrons. But because the number of electrons can change, right? Bullies steal them, wimps lose them. The atom number is the number of protons. You can say, well, what happens when it loses or gains an electron? It's not an atom after that. Okay, it could be a carbon ion or an oxygen ion or a sodium ion, but atoms have an equal number of protons and electrons, so the charge of every atom is neutral. Every atom has no charge. Okay, getting off track a little bit there. Okay, so around the speck of a nucleus is a blur of negativity, and it's negative because there are electrons in it. Electrons are the only thing in the universe with a negative charge. The reason that the electron blur has negative charge is because it's loaded with electrons. There are electrons in there, so it has a negative charge. The whole atom has no charge because the number of protons in the speck of nucleus equals so the positive protons is exactly the same number as the negative electrons in the blur. Okay, and so you might okay, so the blur isn't just a blur. We call it a blur because the electrons appear to move very, very fast, right? We identify their location here, and then a very short period of time later, they're in a different location. And so from that, we infer that they're moving really fast. And when we find them, they always tend to be either this distance from the nucleus, or this distance from the nucleus, or this distance from the nucleus, but not in between those. And so we've given those levels of distance names, and because the ones furthest out have more energy, the electrons further out have more energy, we call those those sort of levels where they might be, right, either close or further away, we call those energy levels. And so that's the structure within the electron blur. And another thing that we've talked about that you should know by now is that even though the electrons are moving really fast and they're really tiny, they don't escape the atom. And the reason for that is they're pulled into the atom because they have a negative charge, and the protons in the middle have a positive charge, and there's an attraction called the electromagnetic attractive force between protons and electrons. So they pull on each other, so the electrons don't escape. And so that force tends to cause them to move closer to each other or toward each other. It's a pulling force. That's different, so then you can say, well, how about, another thing that might happen is in the electron blur, don't they ever crash into each other? Don't they ever collide? And the answer is no, they don't. And the reason is that electrons repel each other. Okay, they tend to move away from each other. They have the electromagnetic force of repulsion. They repel each other. So they move away, that force causes them to move away from each other, so they do not collide. The other example of the electromagnetic force of repulsion is that positive things also repel each other. And you can say, well, then why do we pack all those protons in a tiny area if they're repelling each other? And in the nucleus of an atom, there's another force called the strong nuclear force, and we're not going to talk about that. But that holds the protons together. So what else? Then we've talked about bullies and WIMPs. Okay, so that force of attraction between the nucleus and electrons, and it's really just the outermost electrons that we're talking about, the ones that are furthest from the nucleus. The bullies pull on their electrons harder. Not only theirs, but they can pull on the electrons of other atoms as well. And if that other atom is a WIMP, meaning it doesn't pull on its electrons very hard, then the bully can steal them right away. Steal them from the WIMP. So the bully gains electrons, the WIMP loses electrons. And that's because of the electromagnetic force of attraction. So you might ask, well, why is it stronger in some atoms than others? And the answer is pretty simple. If there are more protons, more positive charge, then there's more pulling force, right? If there's more positivity. And the other thing is, if for its size, is if an atom is smaller, then it pulls on its electrons harder, right? If the distance is less between a nucleus and electron, then the force of attraction is stronger. And so atoms that are bullies tend to have more protons in their nucleus, and they tend to be smaller. So those two things, the smaller distance between the nucleus and the electrons, that makes the force stronger, and more positivity, more protons, that makes the force stronger. So I don't have a timer, but I'm going to stop talking now so I can put this one up. Hopefully it's short enough. Okay, I hope you're all doing well and that this makes sense to you. Remember, if it doesn't, you have a periodic table. There's some information that I haven't taught you how to use yet, but you might be able to figure some stuff out. And there's the exemplar, and you could always pause or go back and watch this again. Okay.